Hello and welcome to this video for Chemistry 20. We are currently reviewing Science 10 Chemistry to make sure, again, students have a strong foundational knowledge to successfully complete the Chemistry 20 course. So in the last lesson, lesson number 3, we talked about naming ionic compounds and elements when they're by themselves. Remember, an ionic compound is made when there's a metal bonded to a nonmetal or polyatomic ions are involved. Molecular compounds, on the other hand, are formed only from non-metal elements bonding together. Now, the bonding that they have is different than what happens in ionic compounds, and we'll learn more about this as we get into the first Chem 20 bonding unit. What essentially happens in ionic compounds is there's a transfer of electrons forming the ion charges that the ions have that make them attract to each other, creating the ionic bond. Molecular compounds, on the other hand, do not transfer their electrons. They actually share their electrons, and the sharing of electrons forms what we call a covalent bond. Covalent bonds are the bonds found in molecular compounds formed by non-metal elements only. There's no metals in these compounds, okay? So what this means is they are not forming ions. They are not in their ion form. Remember, all elements can either be in an ion form or in an atom form. In their ion form, they have ion charges because their protons don't equal their electrons. But when they're in their atom form, they do not have charges. So in a molecular compound, the elements are atoms sharing electrons. This means that we are not balancing ion charges. We're not even looking at ion charges for these compounds, okay? Still, the octet rule is being satisfied because of the sharing of electrons allows them to gain the 8 that they need if they're in energy level 2 or 3 for their valence levels. The duet rule stands for hydrogen and helium having only 2 electrons in their first orbital, and that would be their valence orbital. They would only need 2 to become filled, hydrogen and helium, since their valence level is only the first energy level. But everything else that we deal with, we're going to assume has 8 in their valence levels. Some properties of molecular compounds: when they dissolve in water, they do not conduct electricity unless it's an acid. An acid compound is going to start with hydrogen. It's going to be hydrogen bonded to an anion, okay? Now, in order for, this is a molecular compound technically because the hydrogen shares electrons with the anion, not really acting as an anion until we put it in water. So a hydrogen compound, before it's in water, is considered a molecular compound. And molecular compounds can be solid, liquid, or gas. A lot of hydrogen compounds are gases. When I put it in water, it actually ionizes and becomes like an ionic compound. Okay, so they're going to have ion charges now associated with them. They actually do transfer electrons over in the process, and it becomes ionic, and we're actually going to have its own set of rules for naming acids. So acids are hydrogen containing compounds where hydrogen's at the beginning and they've been dissolved in water. That's what AQ stands for. AQ stands for aqueous. Aqueous meaning it's been dissolved in water. Any type of compound can be aqueous, not just acids. But in order for a hydrogen compound to become acidic, it has to be dissolved in water. Okay, so acids will conduct electricity because, again, they're made of ions, and those ions will dissociate and carry electrical current, but other molecular compounds will not. Like I said, they will either make acidic or neutral solutions, and we talked about the litmus paper tests in the last video. Again, if it's an acid, both litmus papers are red. If it's a base, both litmus papers are blue. And if it's neutral, the red is red and the blue is blue. They stay their original colors. And the states for these are a little more complicated. They can be solid, liquid, or gas. Remember, ionic compounds, their natural state when they're not dissolved in water was always solid. But molecular can be solid, liquid, or gas. It's not something that you're going to be able to predict. Either it's a common compound, and the common compounds are given on your periodic table with their states, or the question will tell you if it wants you to write the state as part of a reaction. So for naming these, we are going to use a prefix system for naming molecular compounds. The prefixes again are on the front of your periodic table: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay? In Chem 30, you will not have those prefixes, so you will eventually have to memorize them. Now the rule is on the first element, we will give it a prefix for how many atoms of that element there are, only if there's more than one, okay? Only if there's more than one atom of that first element. Remember, the prefix for one is mono. So what that means is I will never use mono on the first element. That's just an exception. The second element always has a prefix no matter what it is, and the second element also ends in "ide." Okay? So my first compound, this 2 is after the nitrogen, so it means I have 2 nitrogens. There's an invisible 1 after the oxygen. Okay? So the 2 with the nitrogens gives me a prefix of di, so it's going to be di-nitrogen, again meaning 2 nitrogens, and then monoxide or monooxide, which kind of combines into monoxide. Okay, so mono meaning 1 oxygen, and again it ends in "ide." It's not oxygen, it's oxide. Di-nitrogen monoxide. The next one would be carbon. Again, I'm not using mono on the first element, even though there's one of it. We don't use mono on the first element. The second element always has a prefix, and I have 2 oxygens here, so that would be dioxide. And then the third one I have 4 phosphorus atoms, so that's tetraphosphorus. The first element again just keeps its normal name, tetraphosphorus with the prefix there. And then I have 10 oxygens, that is decaoxide. So tetraphosphorus decaoxide. Okay, the second element again ending in "ide," and notice again how we're not using capitals in the name. It's all small caps. Now, if you're going from the name to the formula, you're again not even looking at ion charges. The prefixes tell you how many to put together. Don't try to balance ion charges or anything like that for these, okay? So for example, because there's no prefix on the first one, that means it had, or it would have had mono, but the rule is not to include mono on the first one. So that means there's 1 atom of carbon, and then there is a prefix on the second element, which is mono, again 1, and oxide is oxygen. So it's 1 carbon and 1 oxygen. Now those are capitals. When you're writing the symbol for an element, the first letter is a capital. So a capital C, a capital O. The next one is again another 1 carbon, because there's no prefix, and tetrachloride. That would be 4 chlorines. So it's CCl4. So carbon is a capital C, chlorine is a capital C, small l, and there's 4 chlorines with your carbon. Okay, notice how I'm not putting the states, because again, it doesn't tell me what the state is, and there's really no way to predict it. A lot of oxides are gases, but you can't always be sure of that, so it's best to not put it unless the question tells you what to put. Now, there is an exception to these prefix rules for naming, and that is if they are a common molecular compound. Common molecular compounds are given in Chem 20 and Chem 30. In Chem 20, it's on the front of your data booklet that we've made for you. You don't have to memorize these, but be familiar with them so that if you were to see NH3, you wouldn't use prefixes to name it. Do not call it nitrogen trihydride. Instead, you're going to call it ammonia. Do not confuse this with the ammonium ion. Okay? The ammonium ion, polyatomic ions will never be by themselves. So if a compound had the ammonium ion, it would be bonded to another element. And in fact, that would be an ionic compound. Okay, but let's say, and this comes up on one of the quizzes, let's say you have NO3. Sometimes students think that's nitrate. That would be the polyatomic nitrate ion if it was bonded to a metal, for example. But when it's by itself, it's actually just a molecular compound, and the name of this would be nitrogen trioxide. Okay, polyatomic ions are never by themselves. So if you think it's a polyatomic ion and it's by itself, it's not. It's just a molecular compound. Okay? Anyway, back to the common compounds. H2O, right, we call that water. We don't call it dihydrogen monoxide. H2S is hydrogen sulfide, also known as sour gas. CH4 is methane. CH3OH is methanol. C2H6 is ethane. C2H5OH is ethanol. C6H12O6 is glucose. C12H22O11 is sucrose. O3, not O2, O3 is ozone. That's what the ozone layer is made of. 3 oxygen atoms bonded together. And then last one, H2O2. There's 2 oxygens with the hydrogens. That is hydrogen peroxide, not water. So notice how the states of these again are given. So these compounds, they're given on the periodic table with their states. So you can always include their states because we know for sure what they are. Okay, next we're going to move on to acids. So as I mentioned before, an acid is a compound that starts with hydrogen most of the time. There's some exceptions that we'll talk about. And the hydrogen is bonded to a nonmetal. This is considered, like I said, a molecular compound. However, when I dissolve it in water, it becomes ionic. It ionizes is the actual term we use for it. Okay? And so what that means is we're going to treat it like an ionic compound. In other words, when I name it, before the compound is in water, I'm going to give it an ionic compound name. Once it's dissolved in water and the state changes to aqueous, then I'm going to give it a proper acid name, which we'll talk about now. So acids again are aqueous, meaning that hydrogen compound is dissolved in water. Okay? Now these are the rules. You're going to, like I said, give your compound, your hydrogen compound, an ionic compound name. Okay? So in other words, we will not be using prefixes to name them. Then, as long as, again, it's been dissolved in water, you change it to an acid name. Now, you can do the ionic name in your head. I like to write it out. Okay? Now, there's 3 rules depending on the ending of the ionic name. So, if it's hydrogen, for example, chloride, it would become hydrochloric acid. If it was hydrogen chlorate, it would just become chloric acid. Same ending, but no hydro beginning. If it was hydrogen chlorite, and I'm just using this as an example, it would become chlorous acid. Okay? So again, let's pretend we have HCl. And that is dissolved in water. So first I'm going to give it an ionic compound name. No prefixes. It would be called hydrogen chloride. Okay? Now actually, if this compound wasn't in water, if this was just HCl gas, that would be your final answer, hydrogen chloride. But if it has the state of aqueous, which means it has been dissolved in water, it also changes to an acid name. Because this ends in "ide", I take this part of the word and put it there. So my hydrogen chloride becomes hydrochloric acid. And that would actually be your final answer, hydrochloric acid, hydrochloric acid. Okay? So you're again using this chart depending on what the ending of the compound name is. Does it end in "ide," which all nonmetals do, and some polyatomic ions? Does it end in "ate" as a compound name, or does it end in "ite"? Okay, and you might have to use this chart backwards also, and when you do, and you're writing the formula for the compound, you do treat hydrogen like an ion, and you do need to balance the ion charge, hydrogen being a +1, and the anion, whatever charge it has, you need the number of hydrogens to balance with it. Okay? So let's look at some examples. Keep this chart in the back of your mind. It's on your periodic table, so pull your periodic table out and follow along. So let's actually do the naming ones first. We'll do 2, 4, and 6. So here I'm going to give it a compound name first. I have hydrogen bonded to phosphate. PO4 is phosphate. Okay? This means as an acid name, I'm going to follow the second rule, which makes it phosphoric acid. Okay, the second rule has an ic ending, no hydro beginning, just an ic ending. Okay, the next one is hydrogen sulfate. I have another ate ending, so I'm following again that same rule. Notice how an OR is brought back into the name. It's not phosphic, it's phosphoric. Same with sulfur. It's not sulfic, it's sulfuric. They add the UR back into the name. They only do that with phosphorus and sulfur. Those, remember, are your two polyatomic elements when they're by themselves. Phosphorus by itself is P4. Sulfur by itself is S8. That's kind of how I remember the ones to add the OR and the UR back into. And then the last one here is hydrogen bonded to carbonate. All three of these follow the same rules. They all ended in ate. So it becomes carbonic acid, ending in ic. Okay? So those are all pretty much the same, but that's okay. Kind of gave you some practice with the ate endings. Let's look at some of the ones going from the acid name to the formula. So when I'm looking at the acid name, I check if it starts with hydro, this one does, and ends with ic. So that means it came from, and don't forget, a lot of times students forget the hydrogen. It's coming from hydrogen and then iodide. Hydrogen iodide. It came from the first rule because it was hydroic. So hydrogen has a 1+. Iodide is iodine as an anion, which is -1. So to balance those, I need one H with one I. Now, I do need to write that this has been dissolved in water, otherwise it wouldn't have the acid name. So I do have to put aqueous after it. Okay? The next one, nitrous acid. I have an us ending and no hydro beginning. That follows the third rule, meaning this compound was hydrogen nitrite. It ends in ite, the third rule. So hydrogen again being H with a 1+, nitrite is NO2 with a -1. So this would be just one of each needed, and again aqueous. And then the last one, hypochlorous. Hypochlor something is actually the name of the ion bonded to hydrogen. It's not a hydro beginning, it's hypo, which is actually the name of the ion. So again, it's hydrogen. Notice they all have hydrogen. Hydrogen, 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 hydrogen. Okay? The hydrogen here is bonds to an ion called hypochlorite. That's the name of the ion. Hypochlor is the root of the word, and it ends in ite. So hydrogen is H. Hypochlorite is OCl-1. So to write the formula for that, again, they balance, but I do need to write aqueous, dissolved in water. Okay? So again, if I had a compound like H2SO4 gas, and I was asked what type of compound that is a molecular compound. When I put it in water, it becomes an acid, but before it's a molecular compound. But because it's not in water, I'm just going to leave it with its ionic compound name. Even though it's not an ionic compound, we follow the ionic compound naming system. Do not use prefixes. So this would just be hydrogen sulfate. I wouldn't change it into an acid name because it's not aqueous. It's not yet dissolved in water. Okay? Now, acids where the H is at the end. If you have the acetate ion, any polyatomic ion that has COO in it, they're organic acids, and they show the order that the atoms are bonding to each other, sharing their electrons. And so because it has a -1 and hydrogen has a +1, the hydrogen is written actually at the end. Okay? And the name of this would be acetic acid. It's coming from hydrogen acetate, so it follows the second rule, and it's called acetic acid. So this is the hydrogen that's usually at the beginning, but it's written at the end. Same with if you have C6H5COO, there's an H when it bonds to make an acid at the end. That is my pen's being funny again. Benzoic acid. It's coming from hydrogen benzoate, so it becomes benzoic acid. And there's actually another ion. It has a 2 negative charge, OOCCOO. Okay? That is the oxalate ion. Because it has a 2 negative charge, I need 2 hydrogens to bond with it to balance the ion charges. One hydrogen goes at the end and the other one goes at the beginning because there's a COO at the beginning and a COO at the end. The H's bond to the O's, and that's why it's written like that. Okay? This is oxalic acid. So those are the organic acids that you'll see in Chem 20. They have, again, this COO in them. That's when the H's are at the end. Okay? Now, before we finish, there's a quick summary of everything we've done so far. So remember, when you're naming things, you have to first figure out what class, what type of substance do I have? Is it an element? Okay? If it's an element, remember you use the name the same as whatever is written on the periodic table, even if it's diatomic or polyatomic, you do not change it. Remember these diatomic ones? Haber-Finkel is the saying we use to remember the diatomic elements. This is their formula when they're by themselves. Okay? All the other elements are monatomic. You could have a molecular compound if it's made of nonmetals, using a common name or prefixes to name it. Ionic compounds, if it's a metal with a nonmetal or polyatomic ions. Remember, for those naming ones in the last video, you name the metal with the Roman numerals if it's multivalent. Then you name the second ion. If it's hydrated, you include a prefix with the word hydrate. Ionic compounds are always solid. Molecular compounds, notice I said don't worry about the state. Ionic compounds balance ion charges. Molecular compounds don't. And lastly, acids, your hydrogen-containing compounds that are dissolved in water. You treat again like they're ionic compounds, even though they are defined as being molecular because they share electrons. Okay? So this is a little review summary. There's some practice questions in your workbook that give you a mix of all this, like you'll see on your quiz. So make sure, again, the first thing you're thinking of is what class is it in, so you know which rule to follow for either naming or writing formulas. Okay? And that is it for this lesson. Thank you for watching.